Okay, class. So this was by far the most missed problem on this quiz, and it was also the one you had to turn in. And I was hoping to see a lot more spreadsheets. I didn't see actually any. You are going to have to use a spreadsheet on the project, so multiple spreadsheets. So I encourage you to start practicing this because it's going to get here really quickly when you have to turn this in via a spreadsheet. So what I want you to see here is just the visual of this. These are speeds or velocities. These are how at what time these speeds were recorded. So basically what's happening is we're getting up to 30 miles per hour, and then they're giving us 10 mile per hour increments. So this is different for different people. When you were taking your own quiz, they might have different numbers, but it was the same concept. So I've got that plotted in here in Desmos, and don't worry about all the math behind it. I've just got a kind of a way to create a line, right? That's the formula for slope right there, and point slope formula. But anyway, don't worry about that. The thing that I want you to see here is just it's a bunch of trapezoids, and so we're given all these data points, and because it's speeds or velocities, the area under a velocity curve is distance traveled or displacement, and that's what we're being asked to find here. The problem is we're being asked to find how many feet the car traveled in these first 37 seconds. And we're given miles per hour. So the thing that you have to do here is to convert miles per hour to feet per second. Now, one thing you could do is type in convert miles per hour to feet per second, and you would get that conversion rate. You multiply the miles per hour times 1.467-ish. That's one way, but where does this come from? Coming from I'm in miles per hour, so miles on top, hours on the bottom, and I desire feet per second. So I want to replace miles with feet. So that means I need to have feet in the numerator and miles in the denominator, so the miles will cancel away and leave me with feet. And I want the hour to cancel and leave me with seconds, so I need to have hour in the numerator, seconds in the denominator, so the hours will cancel and leave me with feet per second. And what that creates is this factor that I multiply by, 5,280 divided by 3,600, and that number is 1.46 repeating. That's where that value is coming from. So that was needed here to get this into feet per second. And then I just want you to think of it, none of these actually look like rectangles, all right, but let's just extend this one up and make it into a rectangle. If this was a rectangle, the units here are, assuming that we've converted our y-axis to feet per second. The units here are feet per second, and then the units here were seconds. So what is the area units? It's feet per second length times width. Feet per second times seconds. The seconds will cancel, and it leaves me with feet. So the area underneath this curve is feet, the area component. So that's what we're being asked to do here, is find the area, the sum of the areas of all these trapezoids. Now what I did is I just made it into a spreadsheet. So I basically took all these data points that you see here, and I transferred this all over to a spreadsheet. There's my time, there's my speed in miles per hour. So the very first thing I did was convert my speed in miles per hour to speed in feet per second. And you can see what I did is I multiplied by 5,280 divided by 3,600 and drug that all down there and got these conversions. And then I calculated delta t, right? Delta t that I needed for each of these trapezoids, right? And then the area of each trapezoid is delta t times the average of the left side and the right side. So it's this delta t with the average of these two, this delta t with the average of these two, and so on. And so in this column E here, I've got delta t, 2.2 times the average of the sum of these. Add these up, divide by 2. And that's the exact same thing. There's no difference between what I'm doing here and the trapezoid rule. It's just the one that I showed you in the video I made for the trapezoid calculator had the same delta t, so it was divided out. But here I would have the delta t multiplied in each time. So to me, it made more sense because of the delta t's not being uniform width to just do it as a bunch of trapezoids. So this is the area of this first trapezoid that's actually a triangle. This is the area of the second trapezoid, and so on and so on and so on. And then when I sum them up, I get the total area, and that area, because I converted, that area is the distance traveled.